Welcome to Quantum Photonics. Here we are to talk about AI that transforms the way we do science and engineering. And our guest speaker is a recurring speaker who talked about the very exciting, innovative AI. In the past, he talked about, in general, about neural operators, which represent a significant advancement in the field of scientific simulations and engineering design, particularly in overcoming the limitations posed by traditional numerical methods. Neural operators have the potential to transform scientific discovery and engineering by providing fast, high fidelity simulations that can replace or augment traditional numerical methods. Their ability to learn from data, generalize across different conditions, and optimize designs makes them a powerful tool in addressing complex real world challenges. Our guest speaker will be speaking about machine learning on function space and neural operators in that sense. So, I would like to introduce him. Kamyar Azizzadenesheli is a research staff at NVIDIA since the summer of 2022, and prior to his role at NVIDIA, he was an assistant professor at Purdue University, Department of Computer Science from fall 2020 to 2022. Prior to his faculty position, he was at the Caltech, California Institute of Technology, as a postdoc scholar in the Department of Computing and Mathematical Sciences. Before his postdoc position, he was appointed as a special student researcher at Caltech, working on machine learning and control. Researchers at the CMS department at the Center for Autonomous Systems and Technologies. He is also a former visiting student researcher at Caltech. And Kamyar is a former visiting student researcher at Stanford University and a researcher at Simmons Institute, UC Berkeley. In addition, he is a former guest researcher at INRIA in France, as well as a visitor at the Microsoft Research Learning Lab in New England and New York. He received his PhD at the University of California in Irvine. So, I proudly bring to you our guest speaker, Dr. Kamyar Azizzadenesheli.
Oh,
Kamyar, welcome to Quantum Photonics.
thank you, Cecile. Thanks for the introduction, and thanks for having me. And also thanks everyone for joining. I'm happy to talk about this new direction in machine learning today.
Yes, we have the slides at the top of the screen, and we are excitedly awaiting your presentation.
Sure. Okay, great. Thanks. We start the presentation at the moment.
All right. Yeah. Thank you.
Great. Sure. Thanks. Thanks again for the invitation. So during this conversation that we will be having today, I would like to introduce, well, not introduce them. Maybe some of you guys already know about this new direction in machine learning, which is I call it machine learning on functional spaces, and it is basically a new paradigm in machine learning that we need to invest a lot of time in the near future to develop the foundations of it. And I will talk about deep learning on function spaces, which results to this paradigm in deep learning called the neural operator. Before getting to the neural operator and machine learning on function spaces, let's see what we have been doing in conventional machine learning. In conventional machine learning, as you might know, we have studied many domains, from computer vision, like pictures and stuff like that, to speech and text and recommendation systems, Atari games, many of these problems. And in all these problems, the data that we have been dealing with were like finite dimensional objects. For example, for computer vision, the data was 64 by 64 image, and the output was a label, cat or dog, or in recommendation system, same, or in language model or chat GPT that you guys are aware of. The input is a sequence of tokens or basic words, and output is a sequence of words. All of these problems, the data, nature of the data is finite dimensional object for which we try to learn a function which maps the input to output. Okay, so the input is a finite dimensional object, the output is a finite dimensional object. So this has been the focus of conventional machine learning for a long time, for like over almost a century now. And we have developed so many methods from CNN, ResNet, UNet, you name it, AlexNet, and many other architectures, and also many foundations for the machine learning in these domains. However, if you just step back a little bit and look at the departments on campus, let's say just pick a random university. Here I just picked a university who is close to where I live. If I look at the many departments there, I know the computer science department cares a lot about vision tasks and language tasks, but the department of like dermatology cares about understanding subsurface of the skin or surface of the skin. In the department of biology or chemistry, we care about protein engineering or molecular dynamics, which is about the study of how molecules and atoms interact with each other in space and time. In mechanical engineering, similarly, we care about like aerodynamics of cars, planes. In geophysics department, we care about subsurface Earth. If there's an earthquake, how the earthquake evolves. If there's a fault somewhere, how we study it. Basically, the study is about subsurface Earth. In sustainability department, we store, let's say, carbon dioxide in subsurface Earth. In weather forecast or in ocean modeling, ocean department or climate department, we care about like modeling climate. We care about modeling the atmosphere around the surface of the Earth, and so we see like many of these departments around the campus. Majority of them they're not concerned with the fact that your machine learning model can classify cat or dog, or whether your machine learning model can talk. They are dealing with some other types of problems. The domain of the problems that they are dealing with are not text or image. They don't care much about the picture. They're dealing with some other problems that are slightly different in nature. And if you project these departments and this school to industry, almost all the industries cares about these types of problems, from car and automotive industry to I don't know, NASA or spaceships and cars and Apple, like when they care about biosignals. All of these companies are concerned with the type of data that are not in a sense image or text. So let me give you a few examples that what are the types of data. So in all of these domains, the data type is not a finite dimensional object. The data type is a function. For example, if I'm concerned with weather forecast, I care about predicting the weather tomorrow, and the weather tomorrow is represented by a function which is a temperature field of the weather tomorrow. So temperature of Earth tomorrow is a function defined on 2D domain or 3D domain on the surface of the Earth. Or velocity field, I care about velocity field, I care about pressure on the surface of the Earth. All of these things are functions for which I care about spatial and temporal derivatives of them because they should fulfill the laws of physics. I care about integration of them because they are like physical quantities that are needed to be preserved. So all these problems in weather forecast and climate modeling and in ocean models, the data that we are dealing with is function. Similarly in seismology, if there's an earthquake, the wave, which is a spatial and temporal function, evolves in subsurface Earth in a medium, which is Earth, which is represented by a velocity field, which is another function. So even here, you see that the input, the data that we're dealing with, or the domain that we're dealing with, are functions, not finite dimensional objects. This types of examples carry to material science. That when we deform a material, we're dealing with the function of space and time. And fusion, when you deal with the plasma dynamics, same with ultrasound imaging, when you inject ultrasound wave to a tissue, the ultrasound wave migrates in the body and comes back. All of these are spatial temporal functions, and the domain for the ultrasound is also a function defining the velocity structure of the tissue. in aerodynamics of cars and airplanes and gliders on the ocean, or like building engines for these moving vehicles. All of these settings we mainly care about aerodynamics of basically the evolution of the fluid around these objects, which are functions in space and time. And the car itself, or the object itself, is also represented by a continuous function in space, uh, which is the geometry of the object. So for all of these problems and many other that I'm not going to go over, the data and the domain that we're dealing with are functions. Okay, just one thing in the in the slides you will see I visualize these functions, but in the sense of pictures, but it doesn't mean that these are pictures. These are actually functions that we care about, spatial temporal derivatives of them. Okay, so the field of machine learning on function spaces is basically developing the foundation of machine learning for these types of domains. And as you can imagine, these domains are not just popped out like yesterday. These domains have been studied for hundreds of years, and there are many methods, classical and conventional, or I would say traditional approaches to solve these problems, including finite difference method or finite element methods, and finite volume methods, and so many other methods that are developed to tackle these types of problems through modeling these physics problems by through like some basics equations, for example, Maxwell equations, Navier-Stokes equation, thermodynamics equations. So these are like laws of physics that we have in the last many centuries we have developed, and we developed also solvers to tackle these problems, to tackle these real world problems. However, as you know, many of these problems, when we develop solvers for, we run them on supercomputers and take forever to run. Okay, but in order to advance science, we need to speed these types of methods up. And also, you know that if you want to solve any of these science problems in a very highly accurate manner, we need to solve these equations at very high resolution. And as you know, as we increase the resolution of the solver becomes slower and slower. For example, I can solve the equation describing the climate at some resolution, very low resolution of 100 kilometer. And for that, I can get some results fast, but 100-kilometer resolution is not sufficient for me to resolve the true dynamics of the climate, for which we need to increase the resolution. As we increase the resolution, the computation complexity of the traditional method goes high. And for that very reason, we cannot just rely on these types of methods in advanced science. For example, if I want to solve climate modeling at the resolution of 1 meter, which actually considers the presence of clouds, with this pace that the computation and the scaling up of traditional methods are going forward, we need to wait until 2060 to be able to run somewhat reasonable simulations with reasonable accuracy. So as you see, this is like we are at the point in science that we know in many domains, including language and computer vision, we have made a lot of progress in terms of machine learning. But for many scientific computing problems that are very essential to our daily life, from weather forecast to climate model to developing cars and building cities, and many of these types of problems, or net zero climate mitigation problems, all of these problems we need to solve scientific computing problems, but the slowness is actually a bottleneck at the moment. Okay, of course there have been many advances in recent years in terms of advancing the compute machines, like instead of using CPUs, now we can accelerate all of the solvers on GPUs. There are many scaling up and parallelization algorithms people have developed to speed these solvers up. All of these are great, and we need those solely because we need to also feed the machine learning models with the data coming out of the solvers. But we need speed ups that machine learning models give us for these types of problems, and so that is basically the focus of these talk about to build the idea and understanding what is machine learning on function spaces, how we can go by with it in the future development. And one of the main reasons that I'm focusing a lot on this term machine learning on function spaces is to emphasize that any of these domains I mentioned, from climate modeling, ocean modeling, aerodynamics of cars, and many more, each of these are domain of machine learning, and we need to study and develop machine learning methods for these. And I would strongly encourage everyone to not do plug and play. Like, do not just take a computer vision architecture or method and apply it to weather forecasts or anything, any of those sorts. The reason is, like, for each of these domains, we need to design a relevant and specific algorithms and foundations to advance the field. Okay, what is machine learning on function spaces? We saw what was machine learning in conventional sense, which was on finite dimensional spaces. The input was a finite dimensional object, let's say 64 by 64 image, and the output was a label or another finite dimensional object. And when I do machine learning on function spaces, the input is a function, output is a function. For example, for weather forecast, input is a function describing temperature, wind velocity, and pressure of the Earth today. And the output is all these variables tomorrow. So input is a function, the output is a function. And what is the task in learning task here is basically learning an operator which maps the input function to output function. So this machine learning on function spaces is about operator learning. We want to learn an operator which maps the input function to output function. Some of the immediate properties that are needed for such method to be useful and valuable in practice is the input to the data that we are dealing with, like in sense of both input and output, they are given to us at different resolutions and different grids. For example, for weather forecast, some of the data points I have, let's say that the temperature of today might be given to me at like 25 million points, let's say in San Francisco, San Mateo, Santa Cruz, and a few other cities in between is not given to me. So that the data that is given to me at some discretization that is not in my control. And tomorrow data might be in different discretization, and the output that I'm trying to output is also given to me at different discretization for any data point. So I need to, in the field of operator learning, the model that we develop, which is called operator, should be able to take the input function at any discretization or any resolution, and be able to output a function at any discretization at any resolution, and should be able to train on input and output that are provided to us at different discretization and different resolution. This is a very important point, that the model should be discretization, or the operator in principle, in mathematical sense we call it, they should be basically discretization agnostic. And in the field of operator learning, we also need this operator to be outputting a function. Why? Because in science, when I'm dealing with, let's say, weather of tomorrow, I care about the spatial and temporal derivatives of it, because these derivatives are supposed to comply with the laws of physics and navics, so like fluid dynamics and thermodynamics. So these are like things that we actually need for sure in machine learning on function spaces, and in particular in scientific computing, where we are dealing with data that is that follows basically laws of physics. Okay, so now we have a somewhat understanding of what is machine learning on function spaces, where basically the data itself is a function for which we have access to it at some discretization. And discretization can vary from data point to data point, so we don't have control over that. And we want to output a function for which we can compute the spatial and temporal derivatives of it. And also we want to compute the integration over the output function. For example, velocity, I want to square it and integrate over it on the surface of the Earth, such that I can compute the energy. So we need to be able to output a function for which we can also compute integration over. So this is about machine learning on function spaces, and similar to machine learning and finite dimensional spaces, for which we have had neural networks developed for over a few decades. We will have something which is called neural operators, which are basically generalization of neural networks to function spaces. So neural networks are for learning functions between finite dimensional spaces. Neural operators are generalization of neural networks that enable us to learn maps between infinite dimensional spaces, or basically function spaces. What is a neural network? As we spoke, the input is a finite dimensional object, let's say I give the neural network 64 image of a cat, and I output a cat. If I change the discretization and make it like 256 by 256, neural network is no longer applicable. Okay, so neural network works on fixed discretization. It's designed to take input as a finite dimensional object. However, a neural operator, I can provide the image, or I can provide the function representing the temperature of the surface of the Earth at any discretization resolution I need. So that's what is neural operator. The input and output can be at any discretization, and the output should be a function that I can compute spatial temperature. I mean, all sorts of derivatives, and also be able to do integration. Another thing about neural operator that is very important is, as you know, in physics, as I increase the resolution or discretization, I get like my physics converges to a unique physics. Similarly, for neural operator, as we increase the discretization or fineness of the discretization, let's say in weather forecast, I should converge to a unique operator. So these are like properties of neural operators that we want. Okay, so now we said what are the properties we want from a neural operator. Now let's say how we can develop a neural operator. One way to develop a neural operator is like directly by generalizing an existing neural network architectures. So if you consider a multi-layer perceptron for which the input is a finite dimensional vector, we have that finite dimensional vector. We multiply it by a matrix, which is a linear operation, and it gives us another vector, and we apply nonlinearity on top, and we repeat this many times, and it gives us a deep neural network. So a neural network takes an input vector, apply a linear matrix vector product on it, and then pointwise nonlinearity, and then repeat this many times to come up with a deep neural network. Neural operator are exact same thing, with this difference that instead of having input as a finite dimensional vector, we have input as a function, and then we apply and linear operations on function spaces often are integral operators or Green's function integration. So input is a function, we apply kernel integral operator on it, which is a linear operator on function spaces, and then we apply pointwise nonlinearity and repeat this many times. It gives us a deep neural operator. So that's basically how we can develop a neural operator.
Excuse me, Kamyar.
Yeah,
What slide number are we now?
I'm looking at slide number 23. So if everyone can go to slide number 23, the first row. Okay, but for neural operator, the input is function A, and I apply the kernel integration on function A, and outputs another function. Where here the function A receives y as an input, which is the domain of function A, and I can compute the kernel integral operation on it, and it gives me another function which I can evaluate it at any point y, basically. Sorry, at any point x. Yeah, indexing here is a little bit off. It should be w of a of x and b of x instead of y. So that's basically a neural operator, and is the generalization of neural network. So you give an input in neural network, we have a linear operation, and then nonlinearity. In neural operator, given an input function a, we apply linear operation, which is an integral operation in function spaces. Okay, so this is basically the architecture of neural operator. And if you go to slide number 24, we see that kernel integral operation applied on function A, when function A is given to us at some discretization, we can actually compute that integration using Riemann sum integration. Okay, which is like a thing is very common. It's been known for like more than a few centuries. Even Gauss had worked on it. So it's like so basically, given an integration, we can discretize that integration and compute it at any discretization. As you can see, this Riemann sum approximation of this integral converges to the true integral as I increase the discretization. So that's basically the way neural operator are in function spaces are defined, and how they can be computed when the input function is given to us at some discretization, and that's how we can actually implement it. Of course, Riemann sum is not the only Nystrom approximation method to approximate an integral. There are gazillions of ways to compute integrals, approximate integrals. If you have used MATLAB before, there are like the whole language is about how to compute this integration, and there are many algorithms and methods to do that. One of them is actually, we should give credit to Fourier. One of the ways to compute integration of this sort is, I'm looking at slide 25, is using Fourier methods to compute this integration. Okay, so this is basically, you compute the input function, the Fourier transform of the input function, and Fourier transform of the kernel that we have, and we do multiplication we carry this integration by multiplication, pointwise multiplication in Fourier domain, and we do inverse Fourier, and this is the way you can actually get this integration in terms of convolution, which is very useful because Fourier methods are very like useful and basically general when we deal with fluid dynamics problems. Fourier representation gives us a compact representation and is very fast when the discretization is given to us in terms of uniform grids, for which we can use fast Fourier transform, which is FFT, to carry out all the integration, which is very computation efficient algorithm. Okay, so when we train a neural operator on pairs of data points, like input output data sets, let's say I train it for Navier-Stokes equation of some dynamics. Let's say that the resolution of the data is 64 by 64. After training the model at this resolution, I can actually query the model at much higher resolution. So it's like 27. It was supposed to be a movie. 27 was not, I think, when it's PDF. But these are literally what you would see if you train the model at some resolution, and then you can directly query the same model at much higher resolution. Okay. Yeah. So it's to this point, I just laid out the foundation of neural operators. This thing I just talked about is very simplified and core first step development of neural operators in this area. But as you can imagine, for any of the scientific computing domain, from automotive industry, weather forecast, molecular dynamics, seismology, electromagnetic, material design, drug discovery, you name it, any of these domains, we need to actually develop a foundation of machine learning for each of them using the principles of neural operators. And also we should note that neural operators are not architectures. These are basically paradigms of deep learning, and for each of these domains we need to build new architectures for each of the scientific computing problems and domains that we are dealing. Okay. In the next few minutes, I would like to talk, maybe 5-10 minutes, I would like to talk about some of the developments the field have had in developing foundational machine learning for some of the few scientific computing domains, and one of them is for weather forecast that I mentioned. In weather forecast, we have actually 40 to 60 years worth of data that is collected every hour, or sometimes even faster, maybe with higher rate. So it means that we have like a very massive data sets of basically real world data, and we can use that data set to train a neural operator, use that data set and develop a neural operator architecture such that we can train a model which forecasts weather. Okay, so we did something like that, and we call it ForecastNet, which trains using the data collected in the last 40 years of, or not last 40 years, 40 years up to 2017-ish, I think, if I'm not mistaken. So we train the ForecastNet model, which is a neural operator-based model, on this data set, and it allows us to learn to forecast weather. And the good thing about this approach is basically twofold that are very exciting. Is this approach, after it's trained, when we want to forecast weather for tomorrow, it's 45,000 times faster than the traditional method which are based on algebraic equation and partial differential equations, and they need to build a solver for. And they are 25,000 times better in terms of energy efficiency. So it's like very, very nice to develop machine learning models for such problems, scientific computing problems. And the second thing is we are actually training these models on semi-real world data. So it doesn't have that much of a human biases that usually you will see in traditional way of doing science. It's not about just science. In 1970s, in machine learning, we have been developing AI expert models that was fully based on human intuition, and that thing didn't go that far. So it's like better to just follow data and train models that are able to do prediction based on the true nature of data than relying on our human limited like understanding of physics phenomena. For this problem, we have developed like Fourier, basically neural operator method based on Fourier neural operator, which I mentioned up there, the one that was using Fourier method to compute integration. That architecture, we call it FNO, Fourier neural operator. And when we use a spherical harmonic Fourier basis for the integration, that architecture, we call it SFNO, is a spherical harmonic Fourier neural operator, which actually is designed and dedicated to parameterize for problems that are functions on sphere. So for this problem that the data is sphere, you can actually design a specific neural operator architecture here, we call it SFNO, to do better forecast. And it's just amazing, the fact that it's just you can output the solution at any resolution, you can take the input at any resolution, you can train this model on many different data sets of different organizations and different institutions which use different basically discretization. Okay. We all know that when weather forecast says tomorrow is going to rain, it might not rain. So weather is semi-stochastic, and also there's uncertainty. And since this model that I just talked about in the slide number, okay, that's mine doesn't have a number, that I just talked about, these models, since they have like 45,000 speed up, they allow us to forecast future of weather many times for many perturbation of the initial condition, and get a full uncertainty about the future of the weather, like maybe like forecasting weather in like next 2 days. It can give us actually the full distribution of possible events of the future. So these are like benefits of using deep learning models for scientific computing problems. Similarly, in seismology, the subsurface Earth is described by velocity structure, and if I put an earthquake somewhere, I can see how the wave propagates in subsurface Earth, and we have observation on the surface, right? So we have observation on the surface of the Earth, which is basically a bunch of stations that we have on the surface. And we can actually use what we observe on the surface of the Earth to infer what is in subsurface. Okay, so we have many basis stations on the surface of the Earth. We can observe what is happening. Given an earthquake, what observation we have, and we can ask, hey, if we are seeing or we have these types of observations on the surface of the Earth, what could be in subsurface? This is basically an inverse problem, and you can develop a specific neural operator architecture for this problem, for which you can just run a forward model and see what it generates on the surface, and see what should have been in subsurface to observe what we observe on the surface. So these types of methods help us to solve very hard problem in inverse seismology to basically understand subsurface Earth. One of the slides was supposed to be a video, but sorry, I'll try to put the videos out, post a link to the videos. But in one of the levers we have to tackle climate change is basically storing carbon dioxide in subsurface Earth. Okay. So this problem is we inject carbon dioxide in subsurface Earth, and we store carbon dioxide there for thousands of years. This is a way we actually we have active action plan to tackle like climate change and climate. It's a way to do climate mitigation. And for that, we actually develop a neural operator architecture specifically designed for CCS, this is a carbon storage problem, that uses the ideas about a domain, uses domain-specific ideas in this area, which is basically interaction of multi-physics, multi-phase, and multi-scale problem, dealing with chemistry of carbon dioxide going to subsurface and interacting with material, thermodynamics laws because it's hotter somewhere down there, and also fluid dynamics laws. All this combination of all this physics are used to develop this model. And then when we train this model and when we deploy it in the 3D domain at a resolution of 1 meter on big areas of up to like 100 kilometers, and this model gives us 700,000 times speed up over the traditional method. Okay, what does it mean? It means that we can do uncertain quantification and reservoir engineering design that used to take like 30 years, let's say 20 years in 20 seconds. So these are basically the benefits we would get when we deal with scientific computing problems and develop right and proper architecture and foundation for that problem. Is CCS problem solved? No. Is the weather forecast problem solved? No. So these are like the beginning of developing machine learning for these domains, and all the effort and time and compute and energy and genius the whole field has put behind computer vision problems and language models and speech and voice. We need to bring all those types of collections of ideas and efforts to these domains and develop the foundation of machine learning for each of these domains separate. Of course, there is a communication between them, but for each of these domains, we need to develop the foundation of machine learning, and note, we should always note that we have, as expert in machine learning, we should definitely understand fully what is the nature of data, and if the nature of data is not a picture, is actually a function, we should definitely develop models and methods for that. And for that, I'm going to talk to you about slide number 36, for which I'm showing you the molecular dynamics problem, where a molecule evolves in time following the laws of basically Schrödinger equation here. And for this problem, at each time you set the molecule at some place, and it moves as a continuous function in time in space. Okay, so many methods in past, even in machine learning, treated this problem as a time series problem, meaning that given time, the state of the molecule at time step t, I want to predict the state of the molecule at t plus delta t. Okay, this is fine, we can do it, but this approach does not consider the fact that the nature of data is actually continuous function in time. So what we said, okay, this problem is not a neural network problem, it's a neural operator problem. And for that, we need to output a full continuous function in time of the evolution of the molecule. So given the state of the molecule, we predict, or we train and we develop a neural operator model. Here is EGNO, is equivalent graph neural operator, for which given the current state of the molecule, we predict the whole continuous function evolution of the molecule in the future. Okay, same ideas people have used in biosignal. When you wear Apple Watch or Fitbit or any of these devices, when they collect data on a human and we want to predict what's happening in the future, or even like digest the state of the health of the person, the input data, it looks like time series, but if you take a closer look, it's not actually a time series. It's actually time discretized observation of a continuous function in time. And for that, if we treat this problem as a neural operator problems, we gain a lot of improvement in many aspects. And slide number 38, it's another problem, which is among all of these problems are my favorite, but it's another one which is very important. Here, I give you the geometry of the car and ask you what is the aerodynamics of the fluid around the car, and specifically what is the pressure on the surface of the car, or was it drag on the surface of the car. For this problem, this is a new domain. For this, we need to invest a lot of time in machine learning to develop the foundation of it. And this is the early work which we develop a neural operator architecture specifically tackling this problem. And for that, we can actually, given the geometry of the car, we can predict or compute basically the surface pressure of the car. Okay. Slide number 39, I'm not going to go much to the deep details of it, but this problem is about material science, is also another favorite problem of mine, because for this, again, you cannot just plug and play in existing models, and you need to develop a specific architecture for this problem. And here is a 2-scale problem. If you zoom in the blue area, you see many, many grids. Each of those grids is not a pixel. Each grid is a PDE, or partial differential equation domain, for which you need to solve a very hard partial differential equation problem to understand the deformation of this material. Okay, and for that we developed this 2-scale neural operator architecture, which is able to tackle this problem with 10 to the power of 5 speed up over the traditional method. And I need to say that this traditional method that we say we provide this 100,000 times speed up is too slow that it actually takes 100 years to run. So we never ran that thing. So we couldn't even run the traditional method to see how they perform here. The fact that neural operator gave us this 10 to the 5 or 5 orders of magnitude speed up allowed us to solve this problem for the first time, which for us even it took like a few days to solve. It's a very, very complex problem, but if you bring the physics and knowledge of the domain to your architecture design and develop the foundation of machine learning in that area, you can actually tackle this problem. It's basically what is my point. My point is, for any of this domain, please let's together focus on developing the foundation of ML for that problem, and avoid plug and play. Plug and play is okay to get immediate results, but treat each of this domain as a full machine learning domain, and let's develop the AI and science together for the future of basically our society and humanity. So as a conclusion, I think we have seen enough evidence in the last many decades that machine learning is going to help us to solve many problems, and science is not an exception. We should do ML and science all together. It's just not like AI for science. I have it in the conclusion, but it's not AI for science. It's actually AI and science together. We're going to together solve the problems in science. And another thing is, when we deal with any problem in science, we need to, if we're a machine learning person and we are dealing with any of these problems, we should definitely ask ourselves the fact that the data is a finite dimensional object or is a function. And if it's a function, we should definitely develop a neural operator architecture for it, and we cannot use neural network architecture there. And solely because neural operators are generalization of neural networks to function spaces. And always when we deal with these problems, if the initial results are not positive, don't worry. Science is not a one-night thing, as we all know. It just takes time to develop the future. And if the initial results are not that positive or as strong as existing method, just know that existing methods often they have been tuned and optimized for 400 years. And if your method that you just developed in last week or two, it doesn't perform better, it's just not a surprise. But push for it, and we will together develop the future of science. Yeah, thank you, everyone.
Yeah, thank you so much, Kamyar. So, everyone, please try to look at the slides, because these are very important slides, and we'd like to really appreciate your sharing that with us here. And I would like to inform everyone that we are opening the floor for questions. There are already questions on the room chat. We will be reading it in a while. And I would like to introduce our guest speaker again for those who just came in. Of course, he would just like to be introduced as a research staff at NVIDIA, and previously he was a professor of computer science at Purdue University. So yeah, Hansen, thanks for coming. I really appreciate it. I would like to have a special mention for Hansen because we invited you, Kamyar, upon our general discussion on foundation models very much earlier. And Hansen suggested that we try to invite you based on this topic. We are very glad that a lot of progress has happened since you last came here. And yeah, just for the sake of the general audience, I would like to ask you again this question. It was in your slide, but are LLMs not enough to do large language models? Have been really prolific in the past 2 years, and every day I could see a lot of research, maybe uh, 15 or 20 papers from important researchers about this. So, are they helpful? How are they compared to neural operators? I would like to ask that question for the sake of those who just came in and also for the general audience.
Yeah, it's a great question. So in machine learning, any architecture we develop, let's say in computer vision or in language model or any other domain, they would not happen from scratch. We actually, if we in last many years, we have developed a great amount of intuitions in developing architectures in computer vision. For many years, we have been using those types of intuitions to develop architectures for language model, and for last 6 7 years, the developments in NLP, natural language processes domain, also helped us to develop architectures for computer vision. So the things go hand in hand. So any developments in any of the domains in machine learning that we have would help us to develop better architecture for other domains. Okay, so you might know the VITs basically were inspired by developments of LLMs in language models, and we brought, by VM in the community, brought those ideas back to basic computer vision, and now VITs are very prominent methods in computer vision. So it's just intuition we develop in each of the domains in machine learning would help us to develop better architectures and better methods for some other domains. And for regarding LLM, basically the attention mechanism behind them, we are using those ideas, or basically we are generalizing those ideas to machine learning on functional spaces. There are plenty of works recently in neural operators that people developed attention-based architecture for neural operators. So there are many new inventions. One of the work we actually had like 2 weeks ago, I think, at ICML Vienna, was about this, how we can bring ideas from attention mechanism to operator learning, to neural operators. And it's a very important subject, solely because in physics there are problems that you're dealing with, multi-physics problems, and the number of variables and number of tokens in those areas are not fixed. So we need to develop the foundation of transformers and attention mechanism in neural operators. What is the difference between LLM and neural operators? LLMs are basically architectures, and neural operators are basically parallel. Okay, LLMs are architectures in the realm of neural networks, and neural networks are on par with neural operators. So neural networks are mapped between finite dimensional spaces. Neural operators are basically, it's a paradigm of machine learning or deep learning that is about learning maps between functional spaces. So I would not compare LLM with neural operators. I can compare LLM with other architectures in neural networks, but we can bring ideas from LLM and like attention mechanism to neural operators. So these types of things are transferable. And as you can imagine, LLM, the language model, if I train it on language, I cannot apply it on Navier-Stokes equations, because these are like values of temperature, velocity, and viscosity, or pressure. These kind of variables, these are like physical quantities I need to deal with, and neural networks are not applicable for these problems. As therefore, LLMs, which are neural networks, are not applicable to these types of domains unless we generalize them to maps between functional spaces, and that's what the research has been doing in the last few years, to generalize these architectures in neural networks to neural operators, and there have been efforts to develop LLM type architectures, which are attention mechanism based models to neural operators, and they have shown successful stories. But still, we are in the infancy area in this, with this respect.
Yeah, thank you so much, Kamyar. So later I have some other questions which I'm sure will interest our guests. But for the sake of course, people who came here on stage and people who asked questions at the room chat, I would like to give the mic to them. And Hansen, if you would like to speak now, just flash your mic. If you want to speak later, okay. Let's go to Hansen, our moderator.
Yeah,
Hansen.
sure.
Okay, thank you very much, Kamyar. I think I have quite a bit of problem, so we can break it up into maybe 2 or 3 pieces. So at the high level, and then we can, if it gets too long, we can go to other people and then come back to me. So at a high level, I'm trying to understand the essence of it, right? So the neural operator, and also excuse me because I'm getting late, so I might have missed important points earlier. So neural operator, it seems from the PPT, I can understand that you have nonlinear parts and linear parts. The sigma stands for the activation function. That's nonlinear. And then the inside is the kernel function, basically integration in products with kernels. And so that part is actually similar to the normal neural nets. So you inside the activation function, that's the linear transformation, and then outside the transformation, and then your linear transformation, and just iteratively apply that compositionally applying all the operators. And I can understand that basically it's a functional kind of a functional analytic kind of way of dealing with the problem. And so let's say you apply Fourier, whether you apply Fourier kernel or wavelet or the Chebyshev polynomial, it's all in the same vein. So in the highest level, it is, I suppose it's similar to the normal neural nets. And then next level, if you applied specific kernels, let's say, for example, Fourier transformation of Fourier kernel or the spherical harmonics or Chebyshev polynomial, whatever you have, the orthogonal polynomials and all that stuff. So you usually when you do those things, you have let's say a special condition, say boundary conditions, that those specific orthogonal functions would be optimal for those boundary conditions, and you apply that. So I suppose that the reason that you choose a particular linear operator or kernel is fits to the specific, say, boundary conditions. Yeah, I'll stop here, and then I have other questions. I'll first ask these, and then I'll circle back. Thank you.
Okay, yeah, sure, Hansen. Thanks for the question. Also, thanks for, as Cecile said, thanks for making this happen. And one thing before I get to the core of your question, I 2 weeks ago I gave a tutorial at ICML about neural operators. It's like 2 hours tutorial, and I would get the videos are not out. Maybe in 2 weeks they will put it out. I'll link it to Cecilia. Probably we can distribute it here.
Great. It's on YouTube, I suppose.
Yeah. So yeah, ICML posted on YouTube. Will post it on YouTube. but under umbrella of ICML. So it would be on YouTube, and we should definitely go over that. And one of the, so I would,
Definitely.
yeah, I talk a lot about the motivations and stuff there. And one of the things there is related to, Hansen, your point, the fact that neural operator and neural networks are very, very similar. I literally derive, like pen and paper type, derive neural operators from neural networks, and how literally each layer of neural network with small changes in it, you can actually go from neural network to neural operator and make the connection. So that's I think should help everyone. So you realize very greatly that neural operator and neural networks are extremely similar, and there I actually teach how you can go from neural network to neural operator with making small changes. But the only thing you need to make sure that you follow is like you should be careful about how those changes are making your model, which is neural network, which is on finite dimensional spaces, to work on function spaces in a way that is consistent. Okay, and those are like not crazy stuff. It's just few things you need to take care of, and very stuff that some of us even learn in high school, like this trapezoid laws of integration. Some of us learn in high school, some will learn it in undergrad. But it's like literally that level of background is needed to see how we can go from neural networks to neural operators. Regarding the choice of the kernel, you brought up a great point. So the choice of kernel is very important for, I mean, from many point of view standpoints. Basically, one of them is like, if we know a lot about the problem at hand, let's say it's fluid dynamics, and we have great ideas about boundary conditions, and let's say we know that Fourier bases are perfect for this, because also the fact that the existing solvers in that area uses spectral solvers, then we know that, hey, Fourier bases are really good for this problem. And if we use Fourier bases to approximate the integration, the benefit is we're actually putting a lot of implicit bias into the model. It allows us to learn the neural operator with very, very few data points. Those Navier-Stokes equation I showed you, okay, usually when we train a deep neural network model, we need millions of data points. Those Navier-Stokes equation I showed for neural operators, since we were using Fourier bases, which are very relevant for that problem, we actually trained the whole model with 800 samples. So the data efficiency comes for free almost if we use domain knowledge and expertise to understand the problem. If you know that wavelets are the best for the problem you're dealing with, for sure we should use wavelets. If you think any other types of architecture, basis is good for the problem you're dealing with, for sure we should definitely bring those to the picture. Usually when we design these things, we have multiple things in mind. One of them is how relevant is that basis to the problem. Another thing is like how hard is to implement them, and how memory efficient are those approaches. Okay, so these are like things that also should be considered. You can use a basis that is very expressive, but if that implementing that basis takes a lot of GPU memory, you're better off not doing it, because you can use less expressive basis, but use 10 layers of neural operator, and you should definitely do much better than having 2-layered neural operator with very expressive basis. So these are the things that actually very commonly happen in this back and forth, and these are basically, we should choose and pick the basis and this architecture choices based on the domain expertise and knowledge we have about the domain. Sometimes also we develop new bases, new method, and sometimes they actually reduce to the other ones. Let's say wavelet neural operator type methods, if you write them down, the whole integration, they actually reduce to FNO. So if that's happened, then you just directly go with FNO. You don't need to go with other methods. But there are some other settings that this reduction doesn't happen. So if the reduction happens, you would use it. So it's basically, what I'm saying is like, we are in this area, in this field, we are at the moment, we are at the situation of similar to 2010 of neural networks, where if you would have asked me a question, hey, for this problem, what you would use, I would have told you, hey, we don't know, because we haven't developed the field yet. So we are still in that area of infancy that if they give me a problem, I'm like, hey, let's see what we can develop for this problem. We don't have an answer. These days for language and vision, if you ask me a question, hey, for this, if you give me a problem and ask me what architecture you use, I would say, okay, use this architecture or that architecture, you should be fine. But if you would have asked similar question 12 years ago or 14 years ago from me about computer vision tasks, I would probably tell you, hey, we don't know, or we need to still develop things and we are not there yet. We are in that stage in neural operators. If you give me like a new problem, we need to go and study what architecture we need to develop. There might not be even a single architecture at the moment for in the realm of neural operators which are applicable for that problem. One of the examples is like automotive industry setting, where the input is a 2D geometry of the car and the output is a pressure on the car. And at the time we were dealing with this problem, there existed no architecture and neural operator could handle such a problem. So we had to develop something. So basically, long story short, we are in infancy and we need to develop this architecture all together.
Great. So would I be correct to say that if you know nothing about, let's say, a random problem chosen from a reservoir, I would just choose, let's say, the generic neural network, and if I know more about the boundary condition, then I'll choose a specific neural operator with a specific kernel. Would that be correct?
Okay, so that's a great question. To some extent, yes. If I have no idea, no structure about the problem at hand, one of the immediate thing would be to use this neural operator method that one of the slides I showed, which uses we call it graph neural operator, which explicitly implement the integration without using any of these bases and learn all the spaces based on data. And the kernel inside that neural operator is represented by a neural network. So if you remember, we have had this integration of k of x and y and a of y. That k, or kappa, which is a kernel of the integration itself, can be a neural network. And in fact, the first paper we wrote to introduce the concept of neural operator didn't have any of this Fourier or low rank basis or Babel, none of these things. It was actually, the kernel was parameterized by a neural network and we had a great success with it. So that's one thing. And second thing is, for some problems that structure of the problem is kind of complex, and also the expert don't have great intuition about what basis is good, which happens often for actual real world problems, which also happened in the automotive industry problem, that car geometry to pressure on the surface of the car. We actually don't use for many of the layers, except the core layers that are based on FNO, which is Fourier neural operator. We use graph neural operator, for which the kernel was actually parameterized by a neural network. So there are many reasons sometimes to use generic basis. The third reason you might want to use generic basis is the setting that, as you know, in machine learning, as we get more data, we try to remove symmetries and biases in the architecture.
Yeah, like okay. Basically going from AlphaGo to AlphaZero.
Exactly. So there we just did this AlphaGo 3. So AlphaZero 3 also has this thing to just remove the symmetry. So in machine learning, if you give me more and more data, like massive data sets, I would try to not enforce symmetry through the architecture. I would not enforce like domain biases through architecture. So in that case, if you have gigantic data set and if you have good GPUs which are like very memory expressive, then for those problems, we often in machine learning, the wisdom is to avoid these types of basis choices we make with respect to the domain knowledge. So there are a bunch of reasons. Yeah.
Go ahead.
Yeah, I just want to say that there are a bunch of reasons to go away from this domain expert advice of using some basis.
Right. Great. So you mentioned the graph neural net. Would that be the one of the reason? Would that be because also the graph neural net is, you can think of it as kind of a Laplacian operator that kind of embedded in it.
Say one more. Okay, one thing I
With
didn't
the
talk about
graph.
neural network. I talked about graph neural operators. They're different.
Oh, yeah, sorry, graph neural operator. Would that be also, is there a kind of a Laplacian operator embedded in the graph neural network?
So the graph neural operator is literally that kernel we have seen, instead of being represented by Laplace operator, or sorry, Laplace basis, or represented by Fourier basis, is actually represented by an MLP, multi-layer perceptron. So that's basically the architecture in graph neural operators. And
Okay, got it.
yeah, so the difference between, also let me state the difference between graph neural networks and graph neural operators. Graph neural operators, they do integration of that sort I showed, which means that if you have a domain and you want to integrate over it, you integrate over all the points in that. So let's say I want to do integration at point X. For that integration, I would look at all the points Y in the neighborhood of point X in the physical domain, in the metric space. Okay. And if I double the resolution or make the resolution 10 times bigger, the number of points in that neighborhood is going to grow. So I'm connecting that point X to all the points on the grid in that ball around point X. So that's basically what you do in graph neural operator, which represent the Riemann sum integration. That's what we have learned from back in the day. Graph neural networks, each point is connected to its neighbors on the graph. Okay, so let's say you have a graph and each point is connected to its neighbors. If you double the resolution, that point is still connected to its k nearest neighbors. If you make the resolution 1,000 times finer, that point is still connected to its neighbors. And if you continue increasing resolution, as you see, that point is connected to itself. So graph neural networks, in the limit, they converge to a pointwise operator. Okay, for which we use graph neural network in neural operator design the moment we want to compute derivatives. Okay, so there is a paper we have had at ICML which shows that since graph neural networks are pointwise and graph neural operators are like basically integration, we can use graph neural networks in conjunction with graph neural operators to compute derivatives. As you know, in many physics problems, the map from input to output is based on derivatives, not integration. So this actually helps us to capture these types of maps that input to output not only involves the integration, but also involves derivatives. So that's what we use.
Yeah, got you. Yeah. So the reason I mentioned the Laplacian operator is I was thinking of the graph, and then when you go random walk on the graph, basically it's a diffusion problem, and then you summing over the neighborhood, and then basically that's the Laplacian operator. So,
okay, that's one thing.
Yeah,
Let me
that's
add here. So the Laplacian operator you can define on the graph, and you can also define on the metric space, right? So the
right.
graph
Yeah.
itself has a Laplacian operator, but here we are talking about physical domain. So here I care about Laplacian in let's say when I talk about Laplacian on let's say velocity, I don't care about what graph you use. I need to compute the Laplacian on the velocity function. Okay, Laplacian on the graph is defined for graph diffusion problems of like let's say we study disease or epidemiology problems that the data is graph. The data is not a function in space that we care about. So for those types of problems, yeah, Laplacian on a graph matters. But for physics problems, we care about Laplacian physical domain. We literally care about like gradients of the function. So these are like slightly different. And for those problems for the problems in physics, we often care about the Laplacian on the physical domain than the Laplacian defined on the graph theory types problems.
Got you. Okay. And the other problem is question is you mentioned that going from the generic direction, you use the graph neural operator, and then for the problems that you know more, you have more domain knowledge or the more specific knowledge, you use specific operators. or kernels. And so in that direction, the second direction, I was thinking I don't know if you've considered, let's say, for example, actually using symmetry, let's say the conservation of some quantity, let's say, for example, energy or other symmetries, and inject, let's say, equivariant property into the operator.
Yeah, that's a fantastic question. It's a fantastic question. That's actually one of the questions I like a lot about. In computer vision, we were always caring about one type of symmetry, and we developed like years of study to address that symmetry. In physics, in any domain we go, any PD you give me, we get different symmetries, right? So it's very, very important for us to develop similar foundations that we have done for computer vision for each of these domains for any given symmetry. So it's just, as a field, we have a lot left to do, which is phenomenal, which is exciting for scientists and researchers in the area. Regarding the symmetry, so we have studied few equivariance problems. One of them is like in molecular dynamics that I showed. We use neural operator to predict the continuous function in time, and for that, if I rotate the molecules, the solution also should rotate. So it should have equivariance in that sense. And if I shift the molecule, I should also shift the solution of the neural operator. So for that sense, we consider it. We are considering symmetry in other settings of operator learning that we are actually right now working on them. There is another work that uses Lie symmetries and they try to incorporate those into architecture. That is through data augmentation, but I haven't seen that many works that actually impose the symmetry directly into architecture, except that equivariant neural operator that I talked about. The rest of the works they do these types of symmetry. They impose symmetry by data augmentation. Let's say you're dealing with Navier-Stokes equation in 3D. If you make the whole thing upside down, the still same thing should work. Like this type. So therefore, when you train a model, you can actually augment your dataset with the same dataset but upside down version of it. So I've seen these types of works that people have developed. But putting it in architecture, one of them is the one I mentioned. Another one that actually is my favorite is the SFNO, spherical harmonic neural operator. Spherical harmonic Fourier neural operator. In that case, you impose symmetry in the sense in the architecture actually, such that if you rotate Earth, the solution should also rotate. Okay, so that or a shallow water equation, which is like you have water on a sphere, the water moves around the sphere. For that, if you rotate the input, the output should also rotate. So these types of symmetry people have developed, but there are so many other symmetries that the field should develop. We are working on a few other extensions at the moment, but yeah, this is a very open area with very few works with respect to symmetry there. And also FNO, as you know, if the domain is what is called periodic, you can make sure that FNO also becomes periodic. FNO is not by per se for periodic domains, but if you know your domain is periodic, you can actually make small changes in FNO and make that one also be equivariant in to satisfy symmetry with respect to the torus. So these things exist actually.
Right. Yeah. So and also more generally, you can find. I think you also mentioned you said Lie. So you basically can find a Lie algebra for, let's say, if you do a PDE, partial differential equation, and you find Lie algebra in the PDE, and then apply apply the symmetry expressed by the algebra to that PDE. And so are you working on that as well?
Yeah, we're actually working on those. There are many ways to do this. We are doing this also in terms of augmentation, data augmentation, and also some other ways of like basic Pinot-based augmentation. We're working on those. But one of the things that I personally very excited and hope to see more of these is putting this Lie algebra and Lie symmetry directly into the architecture. I just explained a few of the works they do it, but it would be great to see more of the works to actually put this symmetry directly into the architecture, not the augmentation. Augmentation, we can do it
Right.
easily.
Yeah,
Yeah,
that's what I was going to say. I mean, augmentation is basically you produce the extending the data set so that the data set has the symmetry. I would be much more interested in having the neural network itself having inherit or the take on the symmetry.
not a neural
itself.
network, but neural operator.
Neural operator, yeah, sure.
Yeah, me too, me too. I'm very excited to see the works that they impose the symmetry directly into the neural operator architecture, which is okay. I'm not saying that those that do augmentation are not interesting. They're very exciting, very important. That's a very interesting line of research. I personally work on that area as well. But also, I would like to see more of symmetry imposed into the architecture directly.
Right. So that way that you don't need so many training data, and
Yeah, 100%.
much faster.
Yeah, much
Yeah.
faster. Yeah. Also, in physics, we really care about preserving stuff.
Exactly. Yeah. Yeah. Basically, you apply Norden's theorem to
Yeah,
the
100%.
neural operator. Yeah.
Yeah.
Fantastic. And then, so last question. So if you in choosing particular operator or kernels, would it be correct to say that if you, I suppose that neural operators dealing with they apply to nonlinear problems. Let's say if I linearize the nonlinear problem and then I say, well, okay, in this linear version, I would choose, let's say, a wavelet or Chebyshev polynomial or Fourier would be more suitable for this linearized version. Would that be saying that, okay, I would extend this conclusion to the nonlinear problem and then I choose that particular kernel for the
Yeah,
nonlinear problem?
sure. It depends on how we linearize it. If it's Koopman operator-based linearization, we don't know much. Or if it's reduced reduced order linearization by some hand-picked maps, it is very heavily dependent on the way we linearize the problem. But
Yes, of
if
course.
we linearize it and we know that, let's say, Chebyshev is great, then probably it's going to influence our intuition a lot. What would be the best way of doing the learning in the actual physical domain?
Right, yeah, cool. Okay, I'll stop here and then let other people take a
Oh, sure.
chance and then I'll
Yeah,
circle back to me. Thank you so
great
much.
question. Yeah, thank you.
Thank you so much, Hansen, for asking very interesting questions to me as well. And Kamyar, thanks too. So I'd like to, earlier Mustafa had many questions, so I would like to read maybe at least two of his questions for now, and then we'll go to Mo and Kevin, who had been waiting patiently here on stage. So yeah, I will just scroll on the question of Mustafa. The first question. So I think he was asking about yeah, I think he has 12 questions, so I'll read just two. So his question was about the codomain attention neural operator. So the first question of Mustafa is, can you explain how CODA-NO differs from other neural operator approaches for solving multi-physics PDEs? And yeah, I think that's his first question.
Yeah, that's a very good question, Mustafa. Actually, this is Codano was presented at ICML like 2 weeks ago, actually. Oh, very fresh question. I wish I would have. Okay, in the slide, extended the slide. There are slides about Codano. So let me tell you why Codano and what is it. In many physics problems, let's say I give you a real example. Actually, in climate modeling, there are many data sets developed by many institutions from many countries. Okay, and one of the data set has 73 variables or 73 functions defined on the sphere. It comes from one country. Another country has, or another institution from a different country has data which has 12 variables in it. Another country developed a data set that has 24 variables in it. Another institution, in collaboration with few countries together, brought the effort together. They actually solved the problem and they developed a data set of 50 variables, but they only saved 34 variables of it. Okay, so there's same problem of the multi-physics problem, but and the data set that we have access to are basically the data sets of different number of variables. Okay, so the one of them has temperature on the surface of the Earth, velocity on the surface of the Earth, but doesn't have the pressure. Another one has pressure, doesn't have precipitation. Another one has precipitation, but doesn't have. So there's like the data set that we're dealing with, the input to output map that I showed in the neural operator motivation. The input function has many variables in it. The output function has many variables in it. Let's say we go from temperature, pressure, and velocity to temperature, pressure, and velocity. But some data in many cases, we actually don't have like 3 variables as an input and 3 variables as an output. We have different number of variables as an input, different number of variables as an output. So in this case, traditional neural operator architectures that have been developed in the past few years would not apply. Okay, so this CodeNO is an architecture which is based on attention mechanism, which doesn't care, similar to LLM that don't care how many words are in input. You can have 10 words as an input and ask it to output next word, or you can have 30 words as an input and ask to output the next word. Here's the way, one of the ways we extend the ideas from attention mechanism and LLM to operator learning, which we consider each of these variables as a token. But the token, instead of being like the token in LLM that is a finite dimensional object, each token here is a function, which is infinite dimensional object. So when we train, so this basically CodeNO stands for codomain attention mechanism. By codomain means that if I give you a function which maps a domain to some numbers, that those numbers are called codomain of the function. So a function in mathematical sense, if you remember high school, it was like the input of the function was called its domain, and the output used to be called codomain. So codomain attention is like you do attention on the codomain, on the number of variables that are provided to us. So basically there are many problems in the real world that we are dealing with. Multi-physics problems for which we have different number of variable counts, and the CodeNO was designed to tackle these problems. And as you can imagine, for CodeNO, since it can handle changing number of variables, we can pre-train CodeNO on many PDEs. Some of them have 3 variables, some of them have like 6 variables, some of them have 5 variables, some of them have like 2 variables. We can pre-train on all of this, and similar to foundation model, fine-tune the pre-train model on new PD or new domain which we want to fine-tune or is a target domain. So that's basically why the CodeNO was invented, what is the intuition behind it, and what is the difference between CodeNO and the conventional neural operator architectures. Solely it's the fact that it can handle the changing number of variables in the input and also in the output. And it's basically a foundation way to build foundation model for PDs. Without CodeNO, is like foundation model would be a little bit shaky because we cannot have a foundation model that only works on 3 variables. We should have a foundation model in this area that is able to work on many number of variables.
Yeah, thank you, Kamyar. So, yeah, I think Mustafa has a lot of questions, but the succeeding questions that he asked, at least the 2 maybe you have already answered. But I just like to read them, and I'll proceed to the next speaker, Mo. And I think there is another interesting question here from Abdirisak on the room chat, but I will just read the questions and of Mustafa. Can you share concrete examples where CodeNO delivered significant results, and how do you compare CodeNO's performance compared to other PDEs? So, yeah.
Okay, that's a great question. So comparison are multiple folds. Let's talk about accuracy. and data efficiency. So when we train Codano on, so the thing is, I can train Codano on, let's say I care about accuracy on a single PD, but since we have data from multiple other PDs, when we pre-train Codano on that PD, so on those PDs, and then fine-tune on Codano, and we compare it against training a model from scratch, Codano outperforms like the existing neural operator models by a huge margin. And actually there are some examples that we can reach a really high accuracy with like few dozens of samples. So in terms of sample efficiency, it makes our models very, very sample efficient. About accuracy, again, with few number of samples, we can actually achieve much higher accuracy. So from these two sense, it's more efficient. In terms of computational efficiency, as you can imagine, transformers are almost always slower than other methods, so it's slightly slower. But the fact that all these methods provide us with 5 or 6 or like few million times speed up over the traditional solver method, I would not be too concerned about the fact that like let's say Codano is like 10%, 50% slower in terms of computation. The fact that we can get better accuracy is a good sign to continue developing in this direction.
Yeah, thank you so much, Kamyar. So I would like to give the mic to Mo on stage. Mo, are you able to speak?
I am. Thank you. This has been a very fascinating conversation. I'm new to the space of machine learning, relatively new. And I'm newer to me is neural operators. My question are many, but one of the things that you mentioned was MLP. And I was wondering if you've tried like other neural networks, like CAN networks, Kolmogorov-Arnold neural networks, and what does it do for new neural operators? And what
That's
is
a
the
great
relationship? Mhm.
that's a great question. Thanks Mo, for the question. So in neural operators, there are multiple places we use MLPs. One of them is for the encoder, another one for decoder, and also for the kernel. We use MLPs often, but there's some new methods like Kolmogorov based neural networks that recently came out. We haven't explicitly studied those to see whether they provide any advancement here. It's not because we are not interested in those, but solely because MLPs play a very tiny role at the moment for in the current architectures of neural operators. We are very much concerned with integration at the moment than with the projection and lifting operator we have in neural operators. But certainly these are like directions that we should definitely take a closer look. At the moment, I would say the other things that we are okay. So it's like very interesting direction to explore, and we should at some point touch on those and see how much improvement they would introduce to the realm of operator learning, basically. So the two places that they can contribute are the encoder and decoder part, as well as the kernel part. And we should study these advancements at some point. We have not done it yet.
Okay. Just two more questions. Would you expect to have a performance improvement if you use CAN versus MLP? And then the last question is, if I want to learn more about neural operators foundationally, what are some good materials? I know you said you were going to share a talk that you gave earlier, but what are some resources for those who are interested in diving deeper?
Okay, those are great questions. So for the first one, I have been following that line of research of Ken, the Kolmogorov based models. I have not yet seen sufficient results that for complex problems they would work very well. as opposed to MLPs. That if I'm waiting for more advancements on these fronts, when the problem that we are feeding these MLPs are complex enough that they can give at least me a huge confidence to use them for neural operators, for developing neural operator architectures. But it's I'm constantly studying those, and I'll be talking to many of experts in the next 2 weeks about this, and they're going to teach me a little more about this area. So if we see enough evidence, definitely we should definitely use these methods to develop further architectures in neural operators. So it's just solely due to lack of my coverage of this area that I'm not sure yet. So I'm keen to learn and understand. Regarding the area to learn more about neural operators. So one of them, as you mentioned, is this ICML tutorial, which hopefully will be out in 2 weeks. Another one is the similar conversation to this we had with Cecilia and the team last year-ish. That Cecilia can allude to that more. It's the second time I'm here talking about neural operators. The previous one also is a great reference. When I was a professor at Purdue, I gave a lecture on that. It's just not okay. Sorry, I should not call it a lecture. It was a crash course. It's a half-an-hour video. That one is also on YouTube on my page. That's, I would say, is like a good half-an-hour time to go over the concept. If your background I'm not talking about more to you, just generally talking to everyone. If anyone has a more on applied math background than ML, more applied math background. Anyone who has more applied math and ML background than just core science. Also, I would encourage taking a look at a paper. We call it Neural Operator something. Is a journal paper we wrote. The link to these papers are on my YouTube video, but let me find it. It's called Neural Operator Learning Maps Between Function Spaces with Application to PDs. This is a good paper which goes through the core of many of the subjects in this area in terms of motivations and advancements and the benefits we have seen so far. There's a Nature paper that we wrote a while back called Neural Operators for Accelerating Scientific Simulation and Design. This is also great. I wrote it, so we wrote it, so I shouldn't say it's great, but it's kind of cool paper too, which goes over the doors that neural operator open to advanced science, and it gives it like a short and try to be also comprehensive address of this subject. So these should be good references to take a look at. Yeah, Cecilia, you were saying.
Yeah, I think we will also post a link to your talks in our website later so that people can try to look at it, like your
Fantastic.
other lecture. Yeah. Thank you so much, Mo. Yeah, we have a lot of people who would like to ask questions, but I think I'd like to give the mic to Kevin now, and after that, I'd like to read the question here on the room chat from Abridisek. And welcome to the stage, Ihab. I hope we have time to discuss more later. So, Kevin, thank you for waiting patiently. Mic to you.
Yeah, hi. Yeah, a lot's been discussed, obviously. So, things I can think of is, well, you mentioned, you have Space Invaders on your first slide. I worked at Atari. I was in the '90s, but anyways, I think you said computers are basically too slow, for this, and if I'm correct, this actually will help quantum mechanics, if I'm correct there, and so it makes me think quantum computers obviously may help in the future, but yeah, since everything's been discussed so much, I can think of those things and just emerging trends or technologies that may be coming to advance, function space operations and interdisciplinary collaborations, like physics, math, engineering. But maybe those are some of the things I can think of right now.
Yeah, fantastic, Kevin. You worked at Atari before? I mean, you were at
Yeah,
the company?
yeah. That was in the 90s. So
Yeah.
that's a quarter of a century ago.
Yeah, so that's fantastic. Actually, I have friends who were at Atari back then. We should talk about that at some point. Like one of the, anyways, I have great friends from back in the day from Atari, and also me personally, I worked on deep reinforcement learning methods for Atari games in like 2000 mid 2020.
Oh
Um,
wow.
yeah, so it's like has been Atari. Okay, whoever maybe those don't know, like Atari games helped a lot in advancement of deep reinforcement learning, and those advancements also helped us to solve problems like AlphaGo. So the Atari was a precursor for that, and Atari emulators have been introduced in 2013 to the field by some of my friends and colleagues in Canada, to which they developed this wrapper around Atari games, and we started building machine learning models on the top of it. And OpenAI, actually, one of the earlier things they have done was developing Atari wrappers. Yeah, so that's a very fun thing. Well, thanks for all the great work, Kevin, for the field. Regarding the question about quantum computing, sorry, quantum mechanics, certainly, like one of the early things we actually were working on, one of the slides I showed also talks about that, how to do molecular dynamics and solving Schrodinger equation using neural operators. So that direction is extremely promising. I'm heavily excited working on that, and very much excited about that direction. You also brought up the work, like collaborative work between engineers, mathematicians, and computer scientists and ML people and all together, which is great thing. And that's one of the things that I would, if you guys have bigger voice, definitely push for it, is to make sure that domain scientists like mathematicians, applied mathematicians, engineers, and scientists in the domain, they do few things. One of them is first of all collaborate with ML expert in their department or in their neighborhood on these subjects, and also understand the fact that ML people don't understand their language. So just bear with the ML folks to understand their language and terminologies, and also help the ML person to also learn ML terminologies. Because these areas are not areas that ML people will develop, and these areas are not the areas that the domain scientists would develop. These areas are areas that the joint collaboration would develop. Computer vision people back in the day did not solve computer vision. ML people also did not solve computer vision. ML people became computer vision people, and computer vision people became ML people, and then we solved the problem. Okay, so these types of problems don't get solved disjointly. And and also in collaboration, if domain experts collaborate with the ML scientists, also make sure that when you try the first few methods, none of them would beat none of them would perform to their desire compared to what they already have. But that doesn't mean that we should stop. We should ask harder questions, and we should develop the solution. The solution is there. We haven't discovered yet. If we are dealing with a problem in science, and we develop a method and we use that method, and the method doesn't work as we desire, it doesn't have the properties that we want, it doesn't mean that the whole field of machine learning cannot tackle that problem, which I have heard a lot, like from domain scientists and domain experts. They say, "All right, ML doesn't work here." I'm like, how do you know? Maybe we just haven't developed a solution to this problem. So these are like the things that are good for both ML scientists and also domain researchers and scientists to know that there are gaps and bridges. There are gaps that we need to bridge first while doing collaboration.
Thanks a lot. Yeah, there's so many people, and I'll try to get a hold of you, see if I can add anything.
Yeah,
Thanks.
sure. Thanks.
Thank you so much, Kevin. And we have Ihab and Rick on stage. However, I'd like to read the question from here on the room chat by Abri Disek, who has been waiting patiently. So, yeah. How can you build? Uh, I lost it. So, can you see it, Darcel? The question of Abri Disek.
Let me take a
The
look.
slide. Oh, go ahead,
Okay.
doctor. Go ahead.
But if you want to read it, just go ahead, carry.
Cecile, which slide is it?
Abri Disek's question,
Oh,
because my app
Actually, I
froze.
found
So,
it. I can read it. I can read it.
oh, you got it.
How
Okay,
can
thank you.
yes,
you? Yeah, sure. Let me read it out loud for everyone. How can you build reservoir models with machine learning if physics parameters such as oil viscosity, temperature, pressure aren't applicable on neural operators to predict oil reservoir recoverable quantities? I'm not quite sure I understand the question. If not applicable, okay, so I think the question is like if there are some parameters like for reservoir engineering, there are some parameters such as oil viscosity, temperature of the field, or pressure aren't applicable on neural operator to predict oil reservoir reserves or recoverable quantities. If they're not, then we sit down and develop a method which makes these things applicable. If the problem mathematically is well defined, we should be able to model it using machine learning. Machine learning is not a magic, right? It's not a mathematical tool. So if the problem is mathematically definable, we should be able to define a machine learning paradigm for that. And if the current architectures are not, they don't support the thing you're suggesting, then we sit down and talk it out and develop a foundation of machine learning for that problem at hand, such that it fulfills the requirement we have. If the model does not receive uh, oil viscosity as an input, then we develop a model which receives the oil viscosity as an input. If the current model doesn't take oil temperature as an input, we develop a model which receives the oil temperature as an input. So basically, it's like if something is there and you think the ML method doesn't work, then we sit down and develop a method which works. So that's I think, if I understand the question. If it is another question asked, then yeah, please correct me.
yeah. Thank you,
I
Kamyar.
think
So, yes, yes, Hansen.
no, yeah, quickly. I think it's not that. I mean, out of the ordinary problem, right? So basically, you get the you combine the Navier-Stokes equation with thermodynamic equation and the state of the equation of state, and yeah, you do this all the time, right?
Yeah.
And then apply whatever method with it, be it a neural operator or any other thing.
Yeah, sure, definitely. If like let's say we have a reservoir engineering problem and we have considered Navier-Stokes and thermodynamics laws, but we didn't consider like laws of chemistry for interaction between material, then we can develop some generalization of Cordano to tackle this problem when we go from these two physics problems to three physics problem by adapting it and developing a new architecture. But as long as the problem that you're dealing with is operating on function spaces, the model which we develop, the machine learning model we develop there is called neural operator. So anytime you're dealing with data that is function, that architecture you develop is called neural operator. And if it's finite dimensional object, you call it neural network. This one just helps the field to distinguish between, understand when someone proposes a method, we at least know what capabilities that method has. Otherwise, we have to go and through whole paper and see what the capabilities have. But if we are developing a machine learning method approach for function spaces, that becomes a neural operator. And if they develop machine learning model for finite dimensional objects, we call it neural network, then we can distinguish between like methods.
Thank you. And yeah, we have Rick here on stage. I just, at this point, I just want to ask you, Kamyar, before giving the mic to Rick. Yeah, we're almost 2 hours here now. So,
Oh yes.
how much more time do you have for us?
Well, the questions were so great that I just lost track of time. If we can just okay, maybe another 5 to 10 minutes. Like at 7ish, I need to leave if you don't mind.
Thank you. So, yeah, I'd like to give the mic to Rick now. Rick, are you able to speak?
Oh, hey, I think you answered my question already. So, just wanted to thank you for um, sharing all this wonderful information with us.
Yeah, thank you for sure. Appreciate it. Thanks for attending and thanks for contributing.
Yeah, thank you, Rick. And I want to just mention this just to inspire, even the general audience that we have. Um, I just want to comment because I think I've read in an article somewhere. Can It's about forecastnet. Is that one of the subproducts of neural operators?
Yeah, indeed. That's actually very interesting work. Yeah, that was actually first work in weather forecast at that resolution that was out, and that was based on neural operators, and that work actually ignited the work of many other folks from different countries and different institutions and different companies, including the works came out of Google DeepMind and Pangu organization or some other institution also made the ECMWF, which is the Weather Bureau of Europe, which actually is the institution provides the weather forecast we use on our phone. Of course, we do local fine tuning on that, but that's an institution which provides like the global weather forecast for all the countries. They all also started to develop machine learning models for weather forecast. So that work actually was the work that it started this or ignited this interest among many people to develop weather forecast models for these problems. And that's also another thing that I emphasize a lot, to make sure that the model you develop is a neural network is a neural operator, not a neural network, is because in weather forecast we are dealing with many different grids, and we wrote this neural operator method like forecastnet version 1 or forecastnet version 2 that it can take any grid and they can work on any grid. But the other works that some colleagues from other places they developed, they are based on neural networks. And the first problem that this weather forecast companies or weather forecast expert in academia have is the accuracy of this model. Others are good, but they are kind of not much use to the experts, because the experts actually need a neural operator, not a neural network, because the data sets they have, they come with a different discretization and different grading. And the other works that came out in the last few years on developing weather forecast methods, they unfortunately both of them, but I wish they would have made their method a neural operator than a neural network. That could have been more useful to the community. But their work advanced a lot towards the direction of weather forecast. So the work of many of the colleagues in this area have been like extremely valuable to advance, and also extremely valuable to us who are doing neural operator design for weather forecast, to learn what are the important components and what are the important steps we need to take to make neural operator architectures work very good in these areas. So yeah, that work has been a very valuable collaboration between many institutions. Is also NVIDIA and many. Also, we had at the time an undergrad student, also was one of the main authors of the work, which is kind of fascinating.
Thank you so much, Kamyar. So I also read about some aspiration that you have about your group has about neural operators moving towards a generalist AI model with emergent capabilities that can simulate any physical phenomena and can generate novel designs that were previously out of reach. So I know that these are early days, but I am very inspired if you have that kind of aspiration as you try to go on progress with your study.
Yeah, that's a great point. It's a great question. The thing is, yeah, we definitely we are working towards that direction. And the challenges that we're dealing with are phenomenally exciting. Like, so generalist AI for language model, fine, it's great. Had many challenges. We have the field had addressed many of those, and we are in a great shape these days. And but when we go to scientific computing domains, the challenges are different flavors, and some of them are actually very interesting. One of the things I sometimes say is these days in scientific computing, we deal with problems that data points are bigger than data sets of conventional machine learning settings. Okay, so let's say you do weather forecast, and I provide you the state of the weather at resolution of 1 meter. Just today's weather and tomorrow's weather, like this pair of data points, can just fill out your whole memory. Okay, so it's like a data point is massive in scientific computing. So developing generalist AI for all sorts of that can tackle all sorts of scientific computing problems is in the horizon. And the challenges in terms from the compute side that we need to tackle are very exciting. And the fact that we don't have a unified or an architecture that we can put out and say, hey, this is the architecture we should develop is another exciting thing. It means that we need to develop many architectures to get to the point that we are confident that we found an architecture that we can rely on. So these are all open problems around, and we are heavily working on those directions. And here and there, we try to expand some ideas towards directly towards foundation models. One of them is this CoDANO approach, co-domain attention mechanism paper for neural operators. That work was one of the works that we actually were like, okay, we have some ideas about operator learning and neural operators. Let's use all of those and develop one semi-generalist AI model for scientific computing. And I think that's one of the things I would probably pursuing, just spend like a year or two, develop many things that I find necessary to be developed for neural operator, and after like a year or two, then come back and bring all of them to develop a new architecture, which is more advanced than the current architectures in CoDANO. So this would be like the thing I've been doing, and I'm very excited about this direction. And also I encourage everyone who is in the area that wants to develop generalist AI in this area, please definitely make sure that the model you develop is a neural operator, because the domain experts actually need something which works on function spaces. If they doesn't, it's just they might be excited, but they get disappointed because they can't use it in their settings. So if anyone works in generalist AI, definitely make sure that you develop something which is in the realm of neural operators to make sure that we work on function spaces. And one of the things actually I didn't talk about it here is the fact that in machine learning, I mean generalist AI that Cecile you mentioned, and LLM heavily relies on data. In physics and scientific computing, the data has two natures to try to basically prospects. One of them is the fact that we have one prospect is the fact that we have the data of pairs of input and output. Another thing is which actually gives us this the supervision for training these models. Another source of supervision, which is a phenomenal thing, and we don't have it in conventional ML methods, similar in computer vision or in language, is the fact that we have access to physics equations. We know that in weather forecasts, if we predict or forecast weather for next 2 days, the upper layer of atmosphere should follow certain physics. Okay, so we can actually use that to further tune and make our model better. So the generalist AI we would have not only should use the data of plain supervised learning data, it also should be able to use the physics laws as another way of getting supervised. And these two sources of data would be the keys to generalist AI. In language model, if your model makes a small mistake, things don't go bad, but in weather forecast, if a model makes a small mistake, we might predict that you're going to have snow tomorrow in San Francisco. Okay, so the mistakes here are non-physical, and we should have generalist AI which also exploit the fact that we have access to the physics laws. So that's another exciting thing, which adds another level of interesting complexity to the development of generalist AI in physics.
Yeah,
I have
thank you,
a
Kamyar. So, I'd like to ask Darcel and Hansen if you want to speak, because we are going to wrap up.
okay. So a couple of question and comment. Have you applied the neuron operator to, let's say, integral differential equation, say a delayed equation? And I have a couple other questions.
That's a good question. We did apply to integral differential equations of like type 1 or type 2. But not. Yeah, I wouldn't say we extensively exhausted the hypothesis there. So there are some studies in those areas, but not a thing that I can basically specifically say. But one of the things we did, which I'm very excited, I'm personally very interested and excited about, is using the ideas from the traditional method or conventional wisdom to solve this integral equations and bringing those to neural operator architecture design. One of the ways to solve these types of problems, as you know, is the multi-pole method or multi-grid method or Galerkin method. And one of the things that I've been working on a lot has been bringing these types of ideas that actually are very prominent in these areas to architecture design. And actually, the second paper in neural operator we wrote many years ago was literally generalizing Galerkin type multiple method and multi-grid methods to the integration we do in neural operators. And the method we came up with was very good and very efficient. And now similar ideas have been used for weather forecast as well as aerodynamics of cars. So the ideas behind all of these methods I'm talking about are actually hidden. Okay, the ideas are in the architecture design of many of these works are actually heavily inspired by methods that the humanity developed in the last few centuries on how to compute integration, in particular, integral equations.
No, I completely would understand, and I completely concur, because basically integral equation method would be a very effective solution for partial differential equations.
Yeah, 100%. And if you've read this book it's called Linear Integral Equations, and this is basically a book by Rainer Karras. And many years ago, a colleague of mine suggested this book. And after reading this book, many ideas for neural operators actually emerged. So the reason we have neural operators these days, one of the reasons is actually this book, which helped a lot to understand how to do integration. and how
Right.
important is
Yeah.
integration.
Yeah. Definitely. What's the author's name again?
Rainer Keres. It's
How do you
called
spell that?
linear. Let me actually have the book in my library.
Oh, okay. If you can put
Uh,
in the chat, that'll
Someone
be
just typed in the
great.
chat.
yeah,
Yeah.
it's called Linear Integral Equations, and the author is Rainer, Rainer, and the last name is Keres, Kress. And the whole book is about how to solve linear integral equations, and integral differential equation set are basically many of the
Yeah.
chapters in this book of type 1, type 2, how you solve them, and also how you solve wave equations, which actually wave equation solution, as you know, and Helmholtz equation actually, as you know, give
How is
us,
expansion Helmholtz?
yeah, it gives us this Green's function integration, which is basically layers of neural operator. The layers of neural
Right.
operator are solution operators of the linear wave equations or Helmholtz
Right.
equations.
It's just the iterative integral. The
100%. Yeah, we
yeah.
just make it
Yeah.
non-linear by make it iterative and
Exactly.
yeah,
Yeah. Insert the activation function
yeah,
in between. Right.
100%,
Yeah.
100%.
Yeah. And the other one is the multiple method.
Yes.
Yeah.
Yeah, multiple method is
So
very, very helpful, very useful. And if you look at the multiple neural operator paper we wrote, if you take a closer look, it resembles UNet. And it was funny in the sense that later, after writing all of these things, I realized that UNet is literally writing down multiple method for finite dimension spaces. We did it for function spaces, but the UNet ID architecture is very, very closely resembling multiple integration methods.
interesting. You mean UNet, right? The
UNet, despite the fact
UNets,
that
right?
it's UNet,
Yeah.
despite the fact that UNet is designed for finite dimensional spaces, but it's very similar to, in nature and idea, similar to multiple method. So that UNet is for finite dimensional spaces, not a neural operator. But in the realm of neural operator, we have multiple neural operator, which is basically generalization of these ideas to multiple ideas to function spaces and our neural operators. And later we wrote a paper called UNO, which is U-shaped neural operator, which is a direct generalization of UNet to operator learning. And then when we put these two close to each other, we're like, hey, these are like very similar to each other, basically multiple neural operator and UNO. And then we realized that, hey, UNet idea is almost identical to multiple integration idea. So these two resulted from, okay, my point is, from multiple idea, we invented something called multiple neural operator. From UNet idea, we invented something called UNO. And when we compared UNO and multiple neural operator, they were almost identical. And we were like, oh, okay. So the UNet and the multiple ideas are actually almost same thing.
Wow, this is fantastic because I didn't know the unit and the relationship between unit and the multiple method. But this is great that you saying basically you're saying you actually developed neural operator from UNet, and then you realize that the multiple method is basically is the same as UNet, right?
Yeah, so basically from multiple integration idea, we developed an architecture called multiple neural operator in 2020. Okay, and from UNet idea, we developed another architecture called UNO, U-shaped neural operator, in 2021 or 2022, I don't remember. But then when we put this two models of basically multiple neural operator and U-shaped neural operator together, we realized that they are almost identical. But we derive each of them from different source, and then after realizing these are almost identical, we realize that, hey, multiple idea from applied math and UNet from 2015 in deep learning are actually coming from similar principles.
Yeah, fantastic. So I'll be quick. one comment is about somebody mentioned, I think maybe Kamyar mentioned CAN, K-A-N, and I actually looked into it, and I found it's hard to discern what the complexity, computational complexity is for that architecture. But yeah, if you
Yeah,
have
that's the main one of the things that I'm actually looking at. The fact that you use the spline there, that's exactly why I said we need to wait to see how it works for more complex problems, where you actually compute matters. For very teeny problems, things work better than NLP. But the question is how things work on problems that are actually very hard. And the fact that it uses many of this simplex method, it's not simplex. I got a brain fog.
Yeah, no, I completely agree. And then quickly, because Cecile mentioned earlier about the weather prediction, and I read about this some time ago, and I have a little bit doubt because maybe it's the usually I haven't looked into the detail of it, but does it like work? Because normally the weather prediction you basically solve Navier-Stokes equation plus the thermodynamics, and it's a huge system of equations, and then you have all the boundary conditions. You have to specify an initial condition, and when people use a neural net or a neural operator, maybe these two are quite different. But my hesitation is that does the neural net basically kind of interpolate the previous solved solution, and then let's say if I have a very different initial condition and boundary condition, would that still be effective?
Okay,
Maybe it's different for the operator and the neural net.
so let me say, yes, as you said, so for the rest of the audience, the weather forecast, as you mentioned, um, as like I think if I'm not mistaken, like 1,200 lines of equations they need to solve, which considers all the laws of thermodynamics and Navier-Stokes and fluid dynamics, and also boundary conditions that you have Mount Everest somewhere. So there are a combination of partial differential equations and algebraic equations. It's a very complex thing. So when the data, we use this this system equation to solve for weather forecast, which is great. But the way these models are trained is we use this solver. Let's call this solver operational model. This solver is able to tell us the weather tomorrow, using this by solving or through solving these equations. But the data that we used to train the model was not a data coming from solver. The data was coming from the real world. So there's this concept called data assimilation. We just look at the observation we have, real world observation we have in San Francisco, Los Angeles, on many stations that we have, sensors and also balloons, satellite data, and all of this together. We use this last 40 years worth of data to assimilate the weather of Earth for last 40 years, and we collected data. It's called Error 5 data. So the Error 5 data is a combination of the solver solution physics basically and the real world data. So the data that these machine learning models are trained, you can think about it as like closer to reality. Okay, so that's one of the advantage of these deep learning models, that you can actually use the real world data to train them rather than as opposed to the solvers that someone needs to go and look at the data and tune the parameters of it. So one of the benefits come from the fact that these machine learning models are directly trained on the data coming from the observation plus the solver. So that's one reason these models work better. regarding the machine, it's a deep regard the question related to neural operators and neural networks. One thing I should say, neural networks, the paradigm reduces to neural networks if we work on fixed grid. Okay, so I need to also say that all those methods that are neural network based, as long as we work on fixed grid, they are okay, and they actually become a special case of neural operators. And the reason they work is the fact that they are directly training from the real world model, and also they are much faster. The only caveat of, okay, not only, one of the main caveats of having neural network approach for this problem is the fact that Error 5 is on lat long grid provided to us, to the world. Also, the same data set is provided in Gaussian grid, meaning that the grid changed. So if you train a neural network on lat long grid, that model does not apply to any other grid. And weather agencies don't have just one data set called Error 5. They have Error 5, they have Icon data set, they have, I don't know, many other data sets they have internally and also they have regional data set, they have observational data, meaning that they have like data of like maybe San Francisco is not in any of those grids that they have the data for Error 5. So they have so many of the data sets they have is on different grids, and is like data never for them is on regular sense. The cities we have or the sensor stations we have around the world, none of them are on regular grid. So that's the reason that we are basically the expert in the field have a hard time digesting neural network ideas, approaches for weather forecast, solely because the moment they go from Error 5 to another version of the same dataset, Error 5, they cannot apply the same neural network on that dataset because the grid changed. That's one of the main reasons we use neural operator for these problems, because the moment grid changes, neural operator doesn't care. Neural operator is mapped in function spaces. The input and output can be provided at any grid. So these are like the basically general story of the weather forecast at the moment. That's why I'm encouraging everyone to develop a neural operator model such that we don't have these types of issues. That we can train same model on many data sets are available in by many institutions and by many countries.
Right. No, okay. I understand that. Yeah, basically it's the grid independent. Yeah, it's a functional space. But
yes.
that's, yeah. So basically, you're saying that it's a mixture of statistical data and the solving the actual PDEs. Is that right?
Yeah. Error 5. Yeah, it is. Basically, it's somewhat like an inverse problem. I tell you historically, let's say for last year, my sensors tell you that what is the temperature in San Francisco, San Diego, and like Berlin or Shanghai or different places. And you ask, okay, if the temperature was like that and wind velocity was like that in that bunch of these places, and since I know the physics, what would have been the temperature and velocity and stuff like that, and other points that I don't have sensors? So this is basically the inverse problem they solve to come up with the Error 5 data set.
I see. Usually, usually, and also inverse problem would get the to determine the parameters in the PDE, like
yes. So those parameters in the
volatility,
solver, the parameters
diffusion
in the operation,
coefficient.
the parameter is in the operational model. Diffusion coefficients. Diffusion coefficient is the simplest one. They have parameters describing reflection of the cloud. They have parameters describing reflection of the ocean. All these parameters are the algebraic part of the equation I mentioned. And all of these in the last 50 years have been developed by many smart people in this area, from undergrad to PhDs and to professors and researchers. All of them one of the main thing was like how to parameterize these things. And this whole field is called parametrization. It basically says we cannot model Mount Everest. Instead, we parameterize the behavior of it. Okay, so that's the algebraic part.
Yeah,
it's like,
so basically effective, kind of an effective phenomenological model.
Yes,
Right.
exactly. And as you can imagine, the accuracy of the model goes as far as the accuracy of this parameterization. And as you know, these parameterization are almost always inaccurate. And also, as you know, as we make the data go out of the range a little bit,
Yeah,
out of
range. Yeah,
distribution,
exactly.
this parameterization, we either don't know their value or they don't work.
Yeah, absolutely, absolutely.
Yeah, but I'm not
Especially
saying
when
that
you, yeah.
I'm not saying that machine learning model works. I'm saying even the solver method that we're using don't work.
Right. No, absolutely. Because basically, it's reducing. You reduce all the Navier-Stokes thermodynamic equation to a few equations and statistical data. Yeah.
Indeed.
Yeah.
Yeah, so I know that Kamyar said
Yeah.
he'll be off at 7. So I think yeah, there are people who posted some questions, something like some application to a digital twin, which we know that NVIDIA is doing. But I think that we should let Kamyar go for now, or else we won't be able to invite him back because I'm breaking my promises about the time.
No,
So
thanks.
yeah, at this point, I'd like to thank our speaker, Dr. Kamyar Azizzadenesheli. It was really, really an inspiring talk, and also thank you for being giving us a succinct explanation and answering all kinds of questions. So yeah, would you like to have a last message for us before we close the room?
Oh, thank you so much for the invitation, and also thanks for everyone for attending, and thanks also for great questions. It was very enjoyable conversation, and if anyone has a question that I haven't answered or you come up with new questions, definitely feel free to email me. I would be happy to answer. Yeah, thanks. Thank everyone for great conversation and room today.
Yeah, Kamyar,
Fantastic.
please come back here for an AMA sometime. Hansen?
Sure, thanks.
Hansen, did you want to say something?
Oh no, I said yeah. I really appreciate it. Thank you so much. I love the session.
And
Thank you.
side comment, Hansen, let's do a can room soon here in
Yeah,
Quantum.
exactly.
Yeah. And Yakamyar, please come back here in Quantum Photonics soon. And we would like to wrap up now, or else we can't say goodbye. Just like, when you're in a party and the conversation is very interesting, you say goodbye for every hour, but you can't. So, because it was a great, great talk.
Oh,
So,
that's
I'd
good.
like to give the mic to Darcel. Thank you, everyone, for supporting this room. And also Mustafa, those who weren't able to come on stage and had asked very great questions, and Kevin for always being here with us, Rick and Mo and Vincent who are here, and those who aren't here anymore. Thank you so much. See you in the next rooms in Quantum Photonics. Darcel, mic to you to help us close the room.
Thank you, Cecile, and thank you, Doctor, for a great room. To close the room, we're going to start our countdown from lucky number 8. Is everybody ready?
Yeah, good.
Ready?
Ready.
8,
8,
8.
Vincent 7,
6.
Mo 6,
5.
Rick 5,
5,
Kevin 4,
4.
Hansen 3,
3. Wow.
Cecile. I heard that. Cecile dos Eques.
Dos Equis, Ni.
Good doctor, your numero uno. Call out our last number, please.
1, I would say.
Yeah. Thank you so much, Kamyar. Thank you, everyone. Good night, and see you in our next rooms.
Yeah.
Yeah,
Thank you, Kamal.
thank you.
Yeah.
Thank you. Bye.
Bye.